everybody. Today we come to the conclusions of this course. Now, programming and methodology and data structures is a course which can go on till infinity. There is no end to continuing with the techniques of programming. These are evolving techniques. Even nowadays newer techniques are coming up. Therefore, we would like to draw a close and try to recapitulate today the salient features of the aspects of programming methodology and data structures. At the outset, I would like to reiterate one thing. We are trying to solve the problem on the computer, but we must not be dictated by actually what is available in the computer today. Because if we are dictated by what is only available in the computer today, then the process of human creativity in problem solving would go, and this process of human creativity which relates to conceptual problem solving would actually be reduced to trying to write programs in the given architecture. So programming methodology and data structuring has got two totally different aspects. One aspect is the conceptual problem solving aspect, how you would conceptually organize your information, how would a person mentally organize his or her information about a problem, how they would solve the problem. By solving, we have discussed various things about solving. The second aspect is mapping it into the computer language, mapping it into a programming language. Now, all programming languages will not provide you with the facilities that a human conceptual thinking would be like, because we think in an abstract manner, and because of this sort of abstract thinking, we have got abstract structures and conceptual components of problem solving. Now, programming, the paradigm of programming has slowly evolved, and due to this evolution, several such conceptual structures have cropped up in new programming languages. If you look at an assembly language program, you will see that even simple assignment statements, conditional statements, expressions, all of them have to be written out in a very long and difficult manner. Higher level languages which provided you if then else structures, while loops, do loops, and even the concept of arrays started the concept of structuring, which was available in a programming language. But when a person can solve it in his or her mind, these structures, conceptual structures, are always available. And there is a semantic gap between a person's thinking style and the actual implementation language which is provided to a person. Programming methodology and data structures is not related to what is the implementation language only, but it is definitely a very important point to understand what is the implementation language. It is important to translate our thoughts into an implementation language, but it is also important to conceptually structure our thoughts in such a manner that we are able to understand, grasp and grapple with the problem at hand in a more organized fashion. Therefore, what we have tried to discuss in this course on programming methodology and data structures is both conceptual programming methodology, conceptual data structuring, as well as actual programming methodology and actual data structuring. Coming to conceptual structures, what did we look at the first thing in a conceptual structure, conceptual problem solving? We said that the solution to a problem comes into the head of the problem solver in some fashion, and in order to translate it into a step-by-step solution on a computer, certain ideas have to be put into. You cannot say that given n numbers, obviously I can see 3 numbers and I know which is the maximum, but just seeing them and just finding out the maximum visually does not lead to a programming style or a solution to a problem. And while discussing this, we came to the concept of decomposition. So the first and important thing about conceptual programming methodology was the concept we discussed, the concept of the initial definition. And this initial definition, we said, had two parts. There was a base condition, there was an inductive step, and this inductive step had got two phases. Phase 1 was decomposition into subproblems, and phase 2 was recomposition of the subproblems. And we have solved several problems and obtained an initial definition, some solution to the problem. Somehow we have to obtain an initial definition. And we saw that in conceptual programming methodology, in this decomposition, we used the concept of recursion. That is, we called the same problem again. And we have done so many problems, I do not wish to repeat and pick up examples. We have tried to solve nearly every problem that way. And this decomposition, these subproblems, so we had a problem P, either this was true, so we returned a solution, or we broke it up into subproblems. We obtained solutions to these subproblems in the same recursive manner, and then these provided their solutions, and then we had this recomposition step here, and then we solved the problem. So this was our initial definition, a definition by which we were able to define some solution to the problem. Now, what is the advantage of such a conceptual initial definition? The advantage of recursion is, or an induction, is that based on recursion and induction, we can get a proof of correctness of the solution. That is, when we have developed a solution which is recursive in nature, we are also able to provide with that initial definition a proof of correctness. We are guaranteed and we are able to prove that this definition is correct. And that is the first step in conceptual problem solving. The first step in programming methodology. That is, generate an initial solution. You cannot start writing a program if then else loop. How? You are given a problem, and for this problem you have to generate a solution. So you have to generate some initial solution, and this initial solution has to be correct. So the first step we saw in conceptual programming was generate an initial solution and check whether it is correct or not correct, and give a proof of correctness. Now, what were the components of this initial solution? This initial solution, the first thing we had in this initial solution was flexibility. This initial solution was not a rigid solution. This initial solution contained various aspects. We could have interchanged the subproblems. The order in which we did the subproblems did not matter. Also, we put in a generalized conditions like split L into two sublists, non-empty sublists L1 and L2. That is, the flexibility indicated that the initial solution contained several alternative possibilities. And we said that an initial solution has got several alternative possibilities. Split a list L1 and L2 into two non-empty lists, or generate 5 subproblems. Now you can do them in any order. Now which order is the best? So the initial solution is actually not a solution, but a set of solutions combined together in an initial recursive wraparound definition. So that was the first thing. The main criteria here are two. One is you have got some solution to the problem which can be translated into a step-by-step definition, and secondly, you know that what inside it, that the solution is correct. So in conceptual programming methodology, that is the first thing. Here all the data elements, none of them are pointed out. Nobody says that this should be an array. Every data element here is general enough and kept as we have done together as a set. So the second point is flexibility of definition is the first point. Second point is data is kept in most general form. A set, a list. You don't say whether it's an array, it's a linked list of pointers, etc., etc. You just keep it in a general concept. So after you generate this initial definition, which is the nucleus of your problem solving, next came the phase of refinement. So the second phase was analysis of initial definition. In analysis of initial definition, the first thing that we discussed was complexity analysis, and in complexity analysis we argued out various things. One is, given an inductive definition, complexity analysis can be done by using recursive equations or recurrence relations, and we use recurrence relations to obtain the complexities. So the first thing that we used here was recurrence relations. Next, we argued out that since you are working on many computers and each of them has a different speed, the size of the input matters, and we have put in a lot of arguments to argue out that getting exact values is actually not very meaningful. In order to understand why one algorithm will be better than another approach, why making one choice would be making better than another. You remember we have a number of choice points in our initial definition, which is the flexibility, and each of these choices would lead to a different complexity, and we have seen that in order to make a very proper definition, a very proper analysis, we cannot go in for exact analysis because the values of the speeds of computer and other issues are there, and there we came to the concept of asymptotic analysis. And in asymptotic analysis we had the order notation, the order and the lower bound notations, and based on these asymptotic analysis we tried to pick and choose which of these design strategies we will use. That is, based on asymptotic analysis we could make certain choices, and these choices were related mainly to how to balance the split. So based on this analysis of the initial definition, we moved on to the concept of refinement. In refinement of initial definition, we saw how to modify the initial definition to obtain solutions, the exact solutions. One of them based on this was balancing the split. Second, we saw identical subproblems being solved only once by the concept of memorizing, which we saw the concept of dynamic programming. And thirdly, we also saw pruning by branch and bound. These are the three techniques that we have seen in refinement. There are several other techniques in refinement. These techniques of refinement are related to how to improve this initial solution. And what is the criteria for improving this initial solution? The major criteria is reduction of complexity. Reduction of complexity means reduction of time, reduction of space, and since we are moving into, we cannot do it for each and every input, we do an asymptotic analysis and try to reduce the space and time asymptotically in the worst case scenario. So asymptotic worst case analysis was used as the basis or the yardstick for refinement, and complexity, the time complexity came first and then came space complexity, and the techniques that we used were balancing, that is the nuclear space that we had in the initial definition, the possibilities that we had in the initial definition were examined, and algorithmic design techniques came up. Till now we are not really bothered with the programming language that we have to use to solve the problem, because if either there is recursion or there is no recursion, even if there is recursion or no recursion, we can still solve the problem. I hope all of us understand that, but we'll come to this issue a bit later on. But conceptually we will solve the problem this way. The third step after refinement of the initial definition came organization of data elements. In the whole program you had some data, and there were two aspects, and on this data you had some operations. For example, while solving the problem, or maybe the problem itself may be such that your data and its operations are clearly identified. You've got a set of integers and you have to insert new integers and you have to pick up the maximum at continuous points of time. So your operations are insert and delete max. So once you get the solution, you know that these are my data elements, and you also know that these are the operations on these data elements. So now you are left to two things. One is how to store the data, that is in what exact form I will store the data, and so that the complexity of the operations on the data is minimized. And that is where we came to the very important issue of data structuring. Now data structuring relates to one, organization or storage of data, and second, efficient algorithms to operate. Here operate means these operations on the data. So to generate an algorithm you require data structuring, for data structuring you require some more algorithms, and this loop goes on and on. So data structuring means how to organize the data and how to store the data. Now here came very important aspects. is the data static? That is, static means what? Data is inserted, data is there, and your operations do not change, that is, do not add new data elements and do not remove some data elements. So after a certain point of time you can say my data is static, or it is dynamic. Dynamic means data elements are new, data elements are added and data elements are deleted. On a static data set you can modify certain aspects of the data, but on a dynamic set even the whole, some elements of the data may be totally removed and some may be added. So in data structuring we had two very important concepts of data structuring. One was static data, second was dynamic. Now storage, how will we store static data and how will we store dynamic data? And in order to store static data we saw that various structures are available. In dynamic data something has to be done. So there are two aspects here. Other than this, in data structuring there was a conceptual structuring. For example, student information, now the name, roll number, etc., subjects a student has taken, the credits of that subject, the grade a student got for that subject. Now all this for a student we would like to keep. Now you can store them in various ways. You can store all students as an array, you can store all subjects as an array, you can store students and subjects as a separate array, or you can put all students and subjects together. So the next concept was encapsulation of data. That is, when you go to storage of data, how you will encapsulate data. In both static and dynamic you had encapsulation, or in C language terms structuring. These encapsulations were also called structures of data. So how to organize data, which data will be structured with which other data, how will they be linked up, whether they will be static or dynamic, all these issues are very important. And among these issues in data structuring was how they will be linked up so that the functions that operate on them are efficient. And when you come to functions that operate on them, that means data elements are there and they are connected. For example, in a matrix elements may be connected, the row, the next column, or in a list of elements the next. How will we operate on this? For this we saw several such data structures. What is a data structure? It is a set of data and operations, efficient operations, so that efficiently they can be operated upon. And what data structures we saw? We saw stacks, which was first in, first out. It was a linked list, a linked list of elements. And in this linked list of elements we have seen first in, first out, insert in the beginning, delete from the beginning, insert in the beginning, delete from the end, insert in the end, delete from the beginning. These are all the possibilities that you can have. Names you will see in books, stacks, queues and other things. We also saw very important other data structures, binary search trees, balancing of binary search trees, why it is important to reduce the time. So data structuring comes again and again, and we have seen some of them. You will see newer problems, newer data structures will come up, and in some problem which is not known today, which will be defined by its own set of operations, even better data structures will come up. So data structuring was a very important part of algorithm design, and as we have just discussed, in order to get data structuring we need to do good algorithm design. So algorithm design and data structuring, or programming methodology and data structuring. Programming methodology involves algorithm design as well as data structuring. These two together work in hand to develop a program. So these are our conceptual ideas. Now we have to translate them into program. So in a program we have to see what programming language offers. and based on that programming language we have to write our program. Nowadays programming languages offer you recursion, programming languages offer you structures, programming languages offer you dynamic allocation. So all this was not available years ago, and that time, even at that time, conceptual decomposition was there, but the translation had to be different. But today the translation has to be done, can be done in a more elegant fashion. That is, you are now closer to your conceptual programming methodology as with the actual programming methodology as you would do in a language like C, say. Here you are provided with dynamic allocation, you are provided with recursion, you are provided with structure definitions, you are provided with arrays, you are provided with pointers, you are provided with linked lists, and so many other things. So once you come to translating it in a programming language, the conceptual structure has to be adapted to the programming language which is the current scenario. Now tomorrow a language can come up which is much better than C, which allows you to automatically write down more complex structures that you would conceive. And C++ is one language where class definitions, where not only data are organized as a structure, but data and procedures are encapsulated to form a class. Therefore these are more general structures, and therefore conceptual programming methodology has to be understood, and that is most important. Once conceptual programming methodology, which includes algorithm design and data structuring conceptually, is understood better, it is only then, when you have to translate it to an actual language, you come to using the language at hand. But nowadays, since recursion is available, since dynamic allocation is available, and very soon even higher level structures and queries, suppose you are doing it on a database, then you would translate it differently, but your conceptual structuring would rather remain a lot same. Therefore, what I would like to stress is that programming methodology and data structures is understood conceptually. It has two facets. One facet is that of conceptual algorithm design, which involved, as we have seen and as we have studied, initial definition, correctness of the initial definition, understanding the flexibility in the initial definition, analyzing the solution, and trying to generate a refinement of the solution. Over and above this, you can analyze and say whether this is the best possible. Is there anything better than this? Can there be anything better than this? These are issues of complexity theory which I do not want to go in at present. And next, once you have got your conceptual algorithm and data structure, now you translate into your programming language, and if you don't have recursion, you will use a stack and you will implement recursion. If you have recursion, you will directly use recursion. If you have a structure, you will use a structure definition. If you don't, you will organize it in a particular manner. If you have or do not have dynamic allocation, you have to approach the problem in a particular way. I do not want to reiterate all the things that we have done in this whole class, but programming has to be understood as to two or three things. First, whatever you've written must be correct. That is the first and foremost criteria, because if you write something which is incorrect, there is no point in trying anything else. After it is correct, it has to be seen that it is efficient. And in order to see that it is efficient, you have to do a lot of these analysis. And once you have done the complexity analysis in a conceptual manner and done a refinement conceptually, translating it into one or more of these known programming languages, or the one in which you have to translate it to, is not a very difficult task. Finally, you have to remember whether is the best possible. That if you can prove, then you're done. Lastly, but not the least, some people are trying, and we have not done it in this course, is given a final solution. You have to verify whether this translation from the initial definition to the final solution is indeed a correct translation. Verification is a difficult task, and all these together makes the art of programming. Programming is a science. It is such a refined science that it tends to become an art when programs are becoming very, very good programs are written. So I would suggest that these philosophies which we have tried to study in this course be tried again and again till these are imbibed onto a person, so that they are so natural that you do not have to follow the steps. They will come to you naturally, as I expect will come to any one of you. Thank you for participating in this course, and I wish you good luck.